Hello everyone. Today we'll discuss about the fluorescent molecules. Now these fluorescent molecules are also given a name fluorophores. And as you name the absorbing molecule like a chromophores, this nomenclature of fluorophores is introduced for the fluorescent molecules. Let us try to understand the details of the structure which really facilitates fluorescence in organic molecules and the other environmental features or external perturbations to facilitate the fluorescence in organic molecules, and also the role of the external perturbations on the fluorescence, spectral behavior and quantum efficiency. Now to begin with, let's look at the molecular parameters. Now in order to understand the molecular parameters, we need to go through the details of the electronic transitions in organic molecules, and these electronic transitions are very important. They play the role of absorption of photon, and also the second stage we let us try to understand the molecular structural features, which includes conjugation, structural rigidity, substituent groups, donor acceptor groups, and motions in the molecule. They all play a role in the fluorescence behavior of the organic molecules. So now let us go to the organic electronic transitions. Now we know already, we have discussed in detail in the basics what are the different types of the electronic transitions possible. If you take an organic molecule, we have the sigma bonding, pi bonding and non-bond electrons, and these pair of electrons can undergo electronic transition by the absorption of appropriate photon, and these transitions are sigma to sigma star, which is the highest energy, sigma to pi star, pi to pi star, n to pi star. So these are the n to pi star is the lower energy electronic transitions. Now the orbitals that we see, sigma, pi, are the non-bonding. They are all occupied orbitals, and the starred orbitals, they are the anti-bonding orbitals. They are the vacant orbitals. So by absorption of photon, electrons undergo transition from the ground state to the excited states. So the energy order of the electronic transitions are n to pi star, the lower energy, pi to pi star is the next energy, next is the sigma to pi star, the highest energy is sigma to sigma star. Let us try to go through the details. Which are the electronic transitions responsible for the fluorescence in the organic molecule? How do they really contribute to the fluorescence energy levels and so on? Now looking at the electronic transition, as we discussed in the previous view graph, sigma to sigma star, they are the higher energy. They are not really much useful for the routine electronic spectroscopy and fluorescence spectroscopy because their energy is quite high and they are almost in the deep UV region. And next is the N2 sigma star. They are also in the UV region, somewhere around 150 to 250 nanometers, and they also do not show much fluorescence behavior. The two electronic transitions which are responsible for the most of the fluorescence that we observe in organic molecules are pi to pi star, and the lowest energy is n to pi star. And most of the organic molecules show this absorption behavior or absorption transitions, and these transitions show the absorption peaks in the region of 200 to 700 depending upon the molecular structures. And the transitions, if you have in the unsaturated group in the molecule, you can see that quite a lot of conjugation resulting in the long wavelength absorption, which is happening for the pi to pi star band. So these are the two important transitions we'll be discussing in detail: pi to pi star and N to pi star transitions. How do they play a role in the fluorescence spectroscopy of the organic molecules? Now, if you look at the electronic transitions and fluorescence in detail, if you look at the UV absorbed in sigma to sigma star, they are seldom to have the fluorescence by absorbing in the UV region. At this range of wavelength, what kind of behavior you can see in the molecule is deactivation of the excited state, and by kind of a pre-dissociation you will see it. Pre-dissociation is the one which talks about the rupture of the bond after the internal conversion. Now, thus the fluorescence due to the sigma to sigma star is seldom observed. Fluorescence is always restricted to the less energetic transitions, pi to pi star and N to pi star transition. Otherwise, the relaxation from the pi star to pi orbitals, pi star to N orbital, and so on. So this is how you can see that we will be focusing ourselves on these two electronic transitions, how they contribute to the fluorescence quantum efficiency. Now, when you address the question of quantum efficiency to this corresponding transitions, if you look at the quantum efficiency of pi star to pi, otherwise pi to pi star electronic transitions, is always higher than the quantum efficiency of the N to pi star transitions. Now, we also should realize that the molar extinction coefficient of the pi star to pi, or otherwise pi to pi star transitions, are almost like 100-fold to 1,000-fold higher than the N to pi star transition. So which is basically due to the transition probability. When you recall your electronic spectroscopy understanding, transition probability is given by the oscillator strength. Oscillator strength is directly proportional to the molar extinction coefficient. So you can really see that the pi to pi star transitions have the higher transition probabilities and resulting in the higher quantum efficiency also. Now, if you look at the lifetime of the pi to pi star, it is shorter than the N to pi star, and in turn, you can see the Kf, the radiative decay constant, fluorescent decay constant, is larger for the pi to pi star orbital, and which tells you that the quantum efficiency is higher for these electronic transitions. Now, if you look at the other deactivation, intersystem crossing from the singlet state to the triplet state, that is the formation of the triplet state from the singlet state, is smaller for the case of the pi to pi star orbital, and which is also contributing to the higher quantum efficiency of the pi to pi star transition. The reason for that is the energy difference between the singlet and triplet states are larger in the case of pi to pi star orbital. So more energy is required to unpair the electron in pi star excited state. You can see that the overlap of the triplet vibrational level with those of the singlet state is less, and the probability of the intersystem crossing is smaller for the case of the pi to pi star orbital. So overall, if you look at it, pi to pi star orbital is showing a higher quantum efficiency when compared to the N to pi star orbital, and the intersystem crossing efficiency is lower in the case of the pi to pi star orbital. That is how the quantum efficiency is connected with the electronic transition. So now looking at the structural features, now when you have the pi system among the pi orbital that you see it, most of the fluorescence molecule that you observe, they're all aromatic in nature, but there are some few highly unsaturated molecules also known to be fluorescent, and lowest lying electronic states is the pi to pi star in this pi system, conjugated pi system. If you have an heteroatom substituted in this pi system, then the N to pi star becomes the lowest energy. Now you can see that by making a substitution in the aromatic system, you can alter the energy level positions of the N to pi star and pi to pi star. If you introduce an heteroatom, N to pi star becomes a lower energy. Now you can also differentiate these two transitions. This is very important in the organic spectroscopy. Now looking at the pi to pi star and n to pi star, you can differentiate them by measuring the molar extinction coefficients. As we already said, the molar extinction coefficient of the pi to pi star transitions are like 100-fold higher than the n to pi star transition. Now you can also do a solvent effect influence and try to establish which is an n to pi star and pi to pi star transition. But otherwise, one can measure and one can identify the transition simply looking at the intensity of the absorption spectrum of the molecule. So if the higher the intensity, that is the pi to pi star orbital. Lower the intensity, it is the n to pi star orbital. It's like a first hand rule, you can say that. And if you are introducing a conjugation, what really happens to this absorption, you can really see that the increase in the conjugation increases the wavelength maximum. Otherwise, it really shifts the maximum towards the lower energy. You can take the case of naphthalene, anthracene, naphthacene, and pentacene. Now, if you see the fluorescence from this molecule, naphthalene is emitting in the UV region because of the one ring which is additionally present in the anthracene and also in conjugation, that shows the emission in the blue region. Now if you add one more ring, it further increases to green. If you add one more ring, it increases to red region. Like this, you can see an increase in the conjugation always increases the wavelength of the emission. Otherwise shifts the wavelength of emission towards the longer wavelength side. This is an influence of the conjugation on the fluorescence of the pi star orbitals. Now if you are substituting electron donors in these molecules, electron donors like a OH group, OR group, NH2 group, or substituted amine groups, and you can see what is the influence. Now what these groups influence is it induces the enhancement in the absorption coefficient. That means they introduce an additional electron density that really makes the absorption intensity to increase. And you can also see there is a shift in the absorption and emission maxima. So this donation shifts the absorption and emission maximum. And if you carefully observe the absorption and emission spectrum, they are becoming broader and structureless. So when you have more charge density into the molecule, it becomes broader and it is structureless. And if you are introducing a lone pair electron, you see in all these group oxygen, nitrogen, they all have a lone pair of electrons, but they do not affect the pi star character of the absorption spectrum. And whereas if you have these electron non-bonded electron systems into the ring like nitrogen, heterocycles, you can immediately see that the n to pi star become lower energy. By keeping it outside the ring, they do not influence much of the pi to pi star character. Only thing is the absorption intensity increases, absorption and emission maxima shifts, and spectrum of the absorption and the emission are becoming broader and structureless. This is how you can see the influence of the electron donation groups. Now if you look at the lone pair lone pair involved in the pi bond in contrast to the carbonyls, you can also look at the lone pairs present in the carbonyls and heterocyclic aromatic as you see it. And in the case of carbonyl and heterocyclic, your n to pi star become lower energy, whereas here they are not. And in fact, the Kasha has introduced a different nomenclature for this representation. In the case of aromatic amines and phenols, he calls it as a L orbital. It's a completely different behavior, so he calls it as a L orbital also. And you can also observe a significant amount of a charge transfer character into the absorption and the emission peaks, and that makes the emission as quite broad and structureless. So because of the presence of a charge transfer or the charge flow from this lone pair of electron that is present in the donors, oxygen and the OH group, OR group, NH2 groups, NHR and NR2 groups, that really makes them to have the broad band and structureless features of the emission and the absorption peaks. Now you also have the possibility of a twisting of the NH2 groups out of the plane of the aromatic ring. And if you have the more steric groups, for example, if I substitute the R groups into this, it always brings in a out of plane structure possible also. And it can also undergo rotation, and a departure from the coplanarity is pronounced for OR group because of the steric reasons. If you have the OH group, it's almost coplanar. So it is simply because of the steric interaction between the oxygen substituents and the ring substituents that you see, or ring protons that you see, that can make them to go out of the plane also. So you can have your enhancement in the absorption spectrum, shift in the absorption and emission maximum. You can really see a broad absorption in the emission spectrum, and you can have a charge injection into the pi electron cloud, and that really makes you to have the structureless broad emission. And you also have the possibility of the out of planar geometry if you have the NH2 groups or NH substituted groups, and if you have the steric interaction, and you will see that the planarity is lost. These are the general observation you can see in the case of the electron donation groups are substituted in the organic molecules. Now when you go for electron withdrawing groups, where you can consider carbonyl and the nitro groups, and what really happens, many of the aromatic ketones and aldehyde, if we see it, they have the lowest energy as the N2 pi star, and this is very important. And when you have the pi system, when you have the electron donation system like a OH, you have the pi to pi star as the lower energy. When you go for a carbonyl groups and the nitro groups, the N to pi star becomes the lowest energy excited states. And when you have the N to pi star group, and we know that the quantum efficiency of the fluorescence is quite low because of the inter-system crossing is higher, and you can have the very dominant relaxation pathway of inter-system crossing. You can see that the benzophenone has the higher quantum efficiency of the triplet also. Now you can carefully look at the structural features: benzophenone, anthrones, fluorinones, anthroxy. So you can see all these ketones have the N to pi star at the lower energy. Benzophenone is almost like a non-fluorescent, and they have the low other molecules have a lower fluorescence quantum efficiency. Now if you see some of the aromatic compounds having a low-lying pi star fluorinone, and some of the ketones also have the pi to pi star transition, the low-lying transitions, low-lying electronic transitions, low energy electronic transitions. But we generally said when you make a carbonyl group, N to pi star is always low. There are some exceptions also. Fluorinone is one such exception. Some of the aromatics with slightly N to pi star character, and they also depend on the polarity of the solvent. Right? Some of the molecules, they have the solvent dependency. They shift their position with their solvent polarity. Xanthone is one example for that. Now when you make other groups into the molecular systems, other groups like sulfonates, and more than one group, that is the other possibility is, so if you have the sulfonates, what it really facilitates is the enhancement in the solubility of these compounds in water, because sulfonic acid group really is a water soluble functional group, so it really makes the whole molecule less water soluble. the influence of this group on the fluorescence is little, no, it does not affect much of the parent molecule. And there is a little redshift in the fluorescence and a little decrease in your quantum efficiency also. Otherwise, in general, sulfonate does not influence much on the photophysical behavior of the molecule, except that it enhances the solubility of the molecule in water. Now, if we have the donor and the acceptor groups in the same molecule, then it's very difficult to predict whether it is N to pi star, pi to pi star is becoming low energy, and whether the molecule will be low fluorescence quantum efficiency or high fluorescence quantum efficiency. If you have the N to pi star, generally it's a low quantum efficiency of fluorescence. If you have pi to pi star, high quantum efficiency of the fluorescence. Whereas if you have mixed substitutions, then it's very difficult. One such example you can say is the 3-nitro-N-dimethyl aniline, which exhibits fluorescence. And this is very difficult. You have the electron withdrawing group, nitro group, and also you have the electron donating group. And it's complicated to explain what is happening in the molecule. And this is how the substituents in the ring can do it. Now, if we really make other heterocycles like a nitrogen heterocycles, they are the azarine family of the molecules. They are pyridine, phenolane, acridine. Now, if you have one or more nitrogen, your low-lying transitions are N to pi star. And we already said whenever you have N to pi star transition, the quantum efficiency of the fluorescence is quite low. So this really explains why these kind of nitrogen substituted heterocycles show a lower quantum efficiency. And moreover, you can see that the fluorescent characteristics of all these compounds are strongly solvent dependent. And if you take protic solvents always have the possibility of forming a hydrogen bond with a lone pair of electrons that are present on these nitrogens. Then you can really see that when there is a hydrogen bonding and there is an inversion of the electronic states are possible. Now, when you have the hydrogen bonding, otherwise when you dissolve these molecules in the protic solvents, pi to pi star becomes your low energy transition, and quantum efficiency of the fluorescence is increasing it. So you can generally say this: when you take these kind of heterocyclic compounds in hydrocarbons, their quantum efficiency is low. When you take these compounds in the protic solvents like methanol or ethanol, you can see the higher quantum efficiency. Reason for that is hydrogen bonding facilitates the lowering of the pi to pi star transition. And this is what is happening when you go for the nitrogen heterocycles. If you look at the nitrogen heterocycles making a bond with the other atoms like proton, hydrogen, nitrogen is singly bonded to carbons, right? And non-bonding electrons have similar property as the pi to pi star transition. So you almost, if you make a bond with nitrogen, you are losing almost like N to pi star characteristics in the electronic transition. So what you see is of the pi to pi star transition. If you have the non-bonding orbital, you look at the non-bonding orbital becomes perpendicular to the plane of the ring also. That is interesting to look at once you make a bond with the proton. And you can see, for example, indole, tryptophan, carbazole, they're all highly fluorescing molecules. And they have the heterocyclic nitrogen, but only difference is it is having the single bonded carbons, and also it has the bonding with the hydrogen. Now, if you go for the other heterocycles, homologs of the nitrogen heterocycles, you can think of a oxygen and sulfur containing heterocycle. They also behave similar to the nitrogen heterocycles. So you can see the dibenzofuran, thiophene, sulfur analogs. They all behave similarly. And many of the practical fluorophores, if you see it, they all have the oxygen analogs, or otherwise oxygen heterocycles like coumarins, rhodamines, pyronines, fluoresceins, and oxazines, and so on. They're all oxygen. So they have the large number of fluorophores available when you have the heterocyclic substitution. When you analyze the coumarin analogs, So if you see the basic molecule of coumarin, which has a very poor quantum efficiency of the fluorescence. Now if you see the structural features, you have the oxygen heterocycle and you have the carbonyl substitution. So the carbonyl, when you make a substitution, we know that the N to pi star is becoming a lower energy. They always have a low quantum efficiency. The same molecule, if you make a substitutions in the 4 and 7, we already said when you make a acceptor and donors, so you cannot predict your property. Now you can see that the 4 and 7 substitution, donating group, electron donating group, then you can see that this molecule 4 and 7, 4 methyl umbelloferrone is strongly fluorescent, otherwise substituted coumarins are fluorescent. You can also look at the 7 amino coumarins, different functional groups you can substitute it. They are also strongly fluorescent. In fact, coumarin dyes are also used as a very good dye lasers, and because they have the very high quantum efficiency. But basic coumarin is not fluorescent. Its quantum efficiency is quite low, not highly fluorescent. It is fluorescent, but it is not highly fluorescent. The quantum efficiency changes once you make a substitutions in this 4 and 7 positions. Now if you look at the nitrogen analogs, they are also quite similar and they have the similar behavior as you see in the oxygen analogs. Now you can have the other nitrogen analogs. Nitrogen and oxygen together are two different nitrogens. Now you have the 7 and 7 substitution really helping you to have the higher quantum efficiency. The coumarin, this, if you look at it, oxygen and additional nitrogen is there. They look quite similar. If you have you have the oxazolines and they have the 2 nitrogen substitutions in the ring system, so they also have the same behavior. Now if you go to the next family of the fluorescent molecule is the xanthene derivatives. In the xanthene derivatives we can consider 2 basic compounds like rhodamines and fluoresceins. Now if you look at the basic structure, it's an oxygen heterocycle, rhodamine, and your fluorescein is also oxygen heterocycles. Now you can have the variety of substitutions to make a rhodamine derivatives and fluorescein derivatives. Now when you look at the rhodamines, there are 2 important molecules of rhodamines, rhodamine 6G and rhodamine B, were among the first fluorescent dyes used as the laser dyes. And if you compare these rhodamines and coumarin, their wavelength of emission are different, and that is the one difference. In fact, they use the coumarin and rhodamines in the tunable dye lasers. Longer wavelength dye emission is from the rhodamine, little blue emission is your blue region emission, otherwise little higher energy emission is possible with the coumarin dyes. Now rhodamine 6G is again a substitution, different substitution. Now you can compare the rhodamine and rhodamine 6G and you have the different substitutions are possible. Now the third class of the rhodamine is your rhodamine B. 6G and B, you can see that the structural differences between 6G and B, and you have NN dimethyl here, it's only the one NN diethyl here, it's only one ethyl substitution, in this nitrogen group. Now you have 2 here, and this carboxylate is an ester here, it's a carboxylic acid. So you can really see that the rhodamine B and 6G are well-known dye lasers. They are used as a dye laser because their quantum efficiency of the fluorescence is very high. Now if you look at the rhodamine analogs like pyranines, they also have the similar structure, similar fluorescent features, and only difference between rhodamine and pyranines is you do not have the phenyl ring in this group. Rest of them remain the same, so it does not influence the fluorescent behavior much. So fluorescence is basically coming from this heterocyclic nitrogen electron groups and the acceptor groups that you have it. That is the reason why the fluorescence is not influenced much by your phenyl group substitutions. In pyranine, as we see that the carbon atom of central ring to opposite nitrogen produces your oxazines, which are really pyranine replacement of the carbon. You can really make an oxazine derivative also. Now this carbon can be replaced with the nitrogen, that gives you oxazine. It is also well known laser dye, emits in the region of 600 and 750 nanometer region. So it's quite similar, when you make, whether you have a carbon or if you have nitrogen, so they show a similar behavior. So this is what you understand when you have a mixed substitutions of donors and acceptor groups, and you may not see much of the N to pi star taking a lead. Only the pi to pi star is taking a lead. Now if you go through the fluorescent derivatives, the second family of xanthene dyes, fluorescein is well known for its behavior towards the fluorescence sensing. Otherwise, it is one of the early molecules used for as a fluorescent probes, and they use this molecule to probe your leakage of water in the dams, and that was a very early application of this molecule as a fluorescent probe. And fluorescent is also used in a lot of ophthalmology imaging, and they are very important molecule because they are highly fluorescent and in the alkaline form. That's very important. When you deprotonate it, they really show strong fluorescence, and they are also used as a pH sensors. Now you can see the eosine and erythrocene vials. Now fluorescein, if you look at it, and the carboxylate group, when you dissolve it in an acid condition, fluorescence is quite low. When you make it alkaline condition, fluorescent emission is very strong because these two are getting deprotonated. Now when you make a substitution with the heavy atoms, bromides, you can see the eosine, and of course when you make a substitution with the heavy atom, quantum efficiency goes down, and it is still having a higher quantum efficiency. And you can have the bromide substitutions and iodide substitutions. So when you have the bromide substitutions, the molecule is named as cosine Y. If it is the iodine, it is like a erythrocene Y. Now you can compare the quantum efficiency of all these substitutions. As I already told you, when you have the heavier atom substitution, bromide quantum efficiency is lower when compared to the basic fluorescein dye. It is basically sodium salt, that means alkaline medium. And if you go for the iodide substitution, quantum efficiency goes down to 0.14. So that is the way you can see it. Your heavy atom substitution also reduces your quantum efficiency of the fluorescence. Right. So far we were talking about the substitutions, whether it's electron donor, acceptor, or heterocyclic centers in the ring system, the nitrogen, oxygen, sulfur. Now when you have the donor acceptor groups in a molecule, you have another interesting behavior is the molecules can undergo rotation. The groups can undergo rotation, and that they influence the electronic excitation also. So how exactly when you have a donor acceptor influence the excitation? So we'll try to understand the electronic absorption behavior. That is, the excitation of fluorophore induces a motion of an electron from one orbital to another. That is very interesting. Donor acceptor. So donor gives you electron, acceptor takes the electron. So in the initial and final orbitals are separated in space. The electronic transition is accompanied by almost instantaneous change in the dipole moment of the fluorophore. Now you can see that when you have a donor acceptor behavior in the molecule, the dipole moment of the excited state also is larger, and it takes place very faster. This happens when you have the electron donating groups like NH2 groups or N-dimethyl group or OMe groups, which are conjugated. This is very important. Donor and acceptor should be in conjugation. The acceptors groups can be a carbonyl or a nitrile, otherwise a CN group. Now you can see a large increase in the dipole moment of the molecule. So you have a donor group, an acceptor group. When you give light to the molecule, you have a good charge separation. Dipole moment is higher, and consequently you can see that the excited state that is reached by electronic excitation is called as a locally excited state. Otherwise it is called as a Frank-Condon state. It is not in equilibrium with its solvents. When you have the charge distribution happening, and when you have there is an adjustment of the solvent around this molecule, reorganization or the restructuring of solvents, that becomes your equilibrated states. So you will see normally two types of the electronic transitions. Otherwise you will see two types of the electronic excited PICT and the associated rotation. What's happening to the electronic states because of the presence of a photo-induced electron charge transfer and rotation, a new excited state is formed, and this new excited state is called as a TICT states. Now this TICT state is a medium supported. If you have the solvent which is fluidic, which can allow the rotation to take place, then you can see that there is a new excited state is reached. That state is called as a intramolecular charge transfer state, and this charge transfer state is important for this kind of a rotation associated molecules. In this solvent relaxation really helps you, explains very nicely the increase in the redshift of the fluorescence as the polarity of the solvent increases. This is the very important phenomenon associated with the charge transfer and solvent relaxation, and that you can see such kind of a relaxation oriented charge transfer states, a rotational coupled charge transfer state in a molecule like a DMAB and dimethyl aminobenzonitrile. The structure you can see here you have N-dimethyl is a group which is responsible for the rotation. You have a donor group, you have an acceptor group is a nitrile. You have a charge flow from the donor to the acceptor, and there is a rotation. So because of the rotation, you have a new state is formed, and this is an additional state to the what you normally see in the electronic state, and this is called as a TICT state. Now the immediately after excitation, absorption of photon excitation that is taking place is called as a LE state, which is a Frank-Condon state, which you can see a partial charge transfer happening. When there is a rotation, you can see the donor orbitals and unpaired electron orbitals or non-bound electron orbitals are parallel with the pi ring system, and that is really pushing all the charge transfer towards the acceptor. Otherwise this results in a full charge transfer. This is called as a TICT, twisted intramolecular charge transfer state. Now the influence of this on the fluorescence spectra is observation of a new peak in the long wavelength red region, and that is what is normally observed as a TICT emission. Now the electronic states can be illustrated very clearly here. LE state is the vertical transition, which is also called as a Frank-Condon state, and because of the twist associated with charge transfer and twist associated with that will give a new emission. New emission always happens at the longer wavelength. It's a low energy gap electronic relaxation. Now this kind of a CT emission, long wavelength emission, can be observed only in the case of the polar solvents. So this kind of a charge transfer is always supported by the solvent relaxation and polar medium. If you take it in the non-polar medium, you will not see such kind of a TICT oriented charge transfer stabilization. So this is a very interesting behavior to look at formation of a two states when you have coupling a charge transfer and the rotation together. Now if you really look at the rotation associated with the charge transfer, in order to establish rotation is responsible for such kind of a charge transfer behavior, new molecules have been designed, and this is the basic DMABN molecule. In this, the rotation of this nitrogen group can be frozen by introducing the proper linkage with the main ring system. Now you can see the second molecule which is completely freezing the rotation because it's covalently linked, and the third molecule is rotation is freeze, but it is twisted because of the groups that are connected to this. You have a ring system that is connected to nitrogen itself is a twisted orientation. Now if you observe the fluorescence behavior, now you have, in the first case, you have the Le and the TICT emission. Otherwise, two emissions are observed for the first molecule, and for the second molecule there is no rotation possibility, only Le emission is seen, no TICT emission is observed. Here it is in a twisted form. You don't need to have rotation to have the charge transfer. Since it is already twisted form, you see only charge transfer emission, no Le emission is seen. So you can nicely establish that the presence of rotation always gives you a new electronic states and new emission. In turn, one can observe this. Now if you make a large number of TICT molecules, so there it is known for the other group of molecules like a DCM, DCS, and symmetric aromatic molecules like anthracyl and malachite green and aromatic. So now you can nicely see that the malachite green is a non-fluorescent. You can nicely see this. This is completely non-fluorescent. Rest of them are all fluorescent, and you can have a nice relaxation of charge transfer transitions are possible, and also you have the rotations associated with that. And if you look at the rhodamines, the rhodamine family also you have a rotation. You can understand the rhodamine 101 and basic rhodamine structure. You have the rotation associated with this, and if you are freezing the rotations, you can see that the quantum efficiency is increasing. So rotations always reduce the quantum efficiency of the fluorescent molecule. If you lock the rotations either by structural modifications or changing in viscosity, you can enhance the fluorescence quantum efficiency. Now you can make a comparison of the structural features and different kind of a structural features with the oxygen heterocyclic system. Comparing it phenolphthalein, there is no oxygen heterocycle, there is a free rotation associated with this group. Now when you freeze the free rotation, you can see that the fluorescein molecule is highly fluorescent, phenolphthalein is non-fluorescent, malachite green is fluorescent, and rhodamines are fluorescent. So like this, you can really look at how exactly you can introduce the malachite green and rhodamine are analogs. You can compare it, and you can see the fluorescein. Rhodamine is fluorescing, this one is not fluorescing to the extent that you are expecting. Now the rotation can always block the fluorescence. Now you have a heavy atom effects. Heavy atom effects we have already discussed, and these heavy atoms will always reduce your quantum efficiency of the fluorescence. You can compare this bromide, iodide, and so on. Similarly, you can look at both the xanthene families, fluorescein families, and see that there is a quantum efficiency decrease as you are introducing the more number of heavy atoms. You can also look at the external perturbations like temperature. Temperature always alters the quantum efficiency. If you see the decrease in temperature always increases the quantum efficiency, otherwise the quantum efficiency decreases with increasing temperature. So it is always inversely related. Now temperature always deactivates the excited states in a non-radiative mode. In turn, it results in a lower quantum efficiency. Now you can also look at the pH influence of the fluorescence. When you have the alkaline pH, acidic pH, you have a large amount of dependency of the fluorescence on the pH. So you can really see that when you have alkaline condition, you have ionized form and non-ionized forms. So they are all showing a different kind of fluorescence behavior. This can be seen in the carboxylate derivatives as well as in the phenol and aniline derivatives. So you can have the pH influence. They're all well-known pH sensors. If you look at the aniline group, if you protonate, you have the different forms of the if you look at the non-protonated form, you have the aniline in a resonance structure, different resonance structure possible. If you protonate it, you have anilinium ion. So this is the one which really brings in a pH dependency of fluorescence. The last external effect is your solvent effect. Solvent always changes the fluorescence behavior. When you have the solvent as a two parameters, one is the viscosity parameter and also the polarity parameter. Viscosity increase always reduces the rotational relaxation, otherwise in turn non-radiative relaxations and otherwise internal conversions in general, and you can reduce your unwanted relaxations by increasing the viscosity, which will influence or which will enhance your fluorescence quantum efficiency. Now when you go for the solvent polarity, solvent dielectric will also change its fluorescence behavior. We will discuss the entire behavior of solvent polarity in the next session. With that, to summarize, what we have discussed today is fluorescent molecules, different kind of structural features, different electronic transitions, and how exactly electronic transitions are responsible for the fluorescence behavior, and substitutions like donor acceptor groups, how they are responsible for the fluorescence, heterocyclic systems like heterocycle centers containing nitrogen, oxygen, sulfur, how do they behave, and rotational features introducing a new charge transfer states and dual emission observations, and the external perturbations like heavy atom effect, temperature effect, and solvent effects. This is the summary of the discussion that we had today. We will see in the next session. In detail we'll discuss about the solvent polarity.